Welcome to part 2 of the lecture on graph learning. So what we'll be talking in this part is graph embedding techniques. So we saw what graphs are, we saw embeddings for other things as graphs, and what we will now be talking about is techniques for embedding graphs when we need them for machine learning. Now, when we're embedding graphs, we have actually sort of one big challenge, right? So when we were working with embeddings before, so we were working, for example, with text, we were working with images. It was actually sort of easy to fit them into a neural network, right? So we had a 1 or 2 or whatever dimensional structure, but just sort of a linear thing. And we could just nicely feed that into the neural network, which is here on the right. Now, this is actually no longer the case when we are working with graphs. So when we are working with graphs, we have a bit of a problem that we cannot sort of straightforwardly put this into a neural network because we don't have that typical linear structure. So this thing here is not something which you can easily represent in a sort of a line, right? So we cannot easily feed it into our network. Now, traditionally, there are some machine learning methods for graphs, which we will skip in this lecture. And these are methods which sort of try to do a manual feature engineering, for example. So they manually try to extract certain features of the nodes in the graph and feed that into a machine learning algorithm. And very often, these kind of methods have problems with scalability. So they are task-specific, have problems with scalability, and that's why we'll not go into them further, but they do exist. Now, what we will be talking about rather is about basically doing an embedding of knowledge graphs in a vector space. And more specifically, we will be talking about embedding nodes in a vector space. So what we'll basically do is we will take each of the nodes in this graph, right? And for each of the nodes, we will be creating a vector in a vector space. And that vector is something which we can easily feed into a machine learning algorithm. Now, so what we are basically doing is it's also something that's called propositionalization. It is that we create one vector for each entity or each node in the graph. It should be compatible with this traditional data mining algorithms and tools, also other machine learning tools or machine learning networks. Now, the main thing which we want from this embedding is that it preserves the information, right? So it preserves the information which is in the original graph, and preferably, at least for now, we want to have things unsupervised, such that these embeddings which we obtain would be task and dataset independent, right? So basically, they come from a certain graph, but then they should be useful for everything. Besides, as already discussed before, we want to have an efficient computation. So if we get a graph, say, with 5 million nodes, 10 million nodes, we should still be able to do this embedding. And finally, we want to have a low dimensional representation. Again, compared to the original graph, so if the original graph has 10 million nodes and a lot of connections, if you want to represent that with sort of normal vector format that is possible, it takes a lot of space. And what we want to have is rather a low dimensional representation of the same thing. Now, in methods to do this, there are sort of two major visions on how this should be done. And so in the one case, people talk about preserving topology. So they want to keep neighbors close together. So if you have in the graph neighbors, say Europe and Germany, they are connected in the graph by an edge. You want to keep them close together in that embedded space. So their embeddings will be also close to each other. And similarly, Africa and Algeria will be also close to each other in that space. Now, a completely different view is that in that embedded space, you should rather preserve similarity. Right? So it means that similar nodes should be close together. And in that case, you will, for example, have two embeddings, an embedding for Europe and an embedding for Africa. And because they are both continents, they would be close together in the embedded space. Germany and Algeria, because they're both large countries, they would also be close together in the embedded space. And so these two major visions exist. Now, there are also two major targets when you're creating these embeddings, and that's related to the tasks which we talked about before. So one real large group of tasks is improving the original data. So we talked already about these three different ones, so knowledge graph completion, link prediction, and anomaly detection. Another target, another set of targets, is what's called downstream machine learning tasks. And what that really means is that while in the first case and the first set of tasks, you would be improving your original data. You just sort of make embeddings and then put something back. In the second case, you're basically going to have a task which has sort of nothing to do with the graph itself. Okay. And so this downstream task could be, for example, classification tasks, could be clustering tasks, or it could be that you're basically going to use the embeddings as part of a larger process. So you could, for example, have a question-answer system, dialogue systems, translation systems in which you use information from knowledge graph, or even, for example, image segmentation, where you're going to use information from knowledge graph to decide that, okay, I have here, say, a cow. So probably what is behind it is not going to be the sea, right? So cows are typically not in the sea; they are typically in other seeds. Okay, so a big question now is how are we going to do that, right? So because we have that graph, we want to go to these embeddings. So what can we? Well, there are basically three major approaches, right? So the first set of approaches is counting on sort of a translational property. So it means that any relation which exists in the knowledge graph is sort of directly mapped to what should happen in the embedded space. Right? So if you have certain relation in the graph, we want to have sort of the same relation happening inside the embedded space. The second group of methods are based on tensor factorization. So it basically means you make a 3D matrix of all the relations in the graph. We will get back to that, what exactly means. And then we are just going to factorize it. And then factorizing means you're going to basically make a lower dimensional representation of that three-dimensional matrix, also with a lower matrix dimensionality. And then because that has to basically sort of generalize to be sort of squeezed in that small space, so reconstructing that gives some idea on what kind of edges were missing in the original graph. Finally, we'll talk a bit about random walk-based methods. So it means that you're going to have more of you start at a certain node and you start walking around. So you're basically going to look at the context of that node to embed it. And that uses this distributional hypothesis, which we also talked about in the context of word embeddings. So let's go into more detail on these three. So first on the translational ones. Now the translational ones, so there are really a lot of approaches, right? So there are still new ones appearing, and well, basically they sort of all come down to the same thing. So what we will do is we'll basically look at the very first one, so that's trans E, and the other ones are just basically more complex versions of that. So now the core idea of trans E is that you take every edge in the graph. So let's say that we have a large knowledge graph, right? And in the knowledge graph we have these nodes, and we have a typed edge in between it, right? So this is an edge with type E. And so what we are going to do is we are going to say, like, if this kind of edge exists in our knowledge graph, then we want to have it such that in our embedded space we have these two embeddings corresponding to that to these nodes, and we have an translation, an embedding of that edge, which connects these two things. So this is basically a vector. This E is a vector which maps as a translation from that one to that one. So if we then would have a second triple with the same type, then basically that same edge embedding would be used. But then basically, what we basically want to do is we want to make it such that, or what we want to optimize for, is to make it such that if we have that head here of the relation, as it's called, so that's why it's called H, it's the head of the relation. Then we have the edge, and then we have the tail. We want to make it such that if we are adding that embedding of the relation, which is this one here, then we should roughly end up in the tail of the relation. And so basically the thing which we try to minimize is for all edges which we have in our knowledge graph S, we try to make the distance between the sum of these two things, so basically this plus that embedding for the edge, as close as possible to t. So we minimize the distance between these two, between the end of this vector and that entity. That's our goal. Now this is not completely sufficient, right? So this works. I mean, this seems to work, but the problem is that we only have sort of positive information. So what this means is that the model can sort of over-optimize to that, and basically get total nonsense. So what we have to do is we, instead of only saying that it should minimize this distance which we have set here, we should also make sure that it sort of also sort of penalizes if wrong triples or wrong relations in the graph are also being close to each other. So what we have written here as a loss function is basically we take valid triples here. So these are valid. Oops, these are valid triples, and for each valid triple, we also take a lot of what's called negative triples, right? And what it means is basically we take the same. What we have here, this set here. And these are basically triples which are corrupted. It means we take a real triple which exists. A triple, then I mean it's a node, an edge, and another node. We remove either the end of that edge or the beginning, and we replace it randomly by something else. So we basically sort of make a random arrow in the graph. And then we say that that we want to basically minimize the distance if that was a good triple, and we want to maximize if that is a bad triple. And this also has a margin, so it's a margin-based loss. Okay, so these kind of methods have a benefit in that they are conceptually sort of easy, right? So basically, if you have an arrow or an edge in your graph, then you also want to have a corresponding vector in your embedded space which connects the embedding of the entities, which are the head and the tail in your original graph. So conceptually, it's sort of easy. Now, the problem is that this is maybe a bit too easy, so the embedding quality is not extremely high. Now, why are there so many of these improvements? Well, basically, sort of, they become basically better and better. Now, the problem is that the better the model becomes, the less scalable they become, because they just start doing more and more stuff. And now, one sort of issue with these kind of methods is that they typically sort of look only one hop away from each other. So they just in this optimization function, you just have only one hop information. So you just have a current entity, one hop you're doing, one relation you're traversing, and then you're in that node, but you're not going much further. Recursively, it somehow gets that information as well, but still not very well. Another group of methods is around matrix factorization. And so we will look at one canonical example of matrix factorization, and there are a lot of more approaches as well. So the one we are looking at is this called RESCAL, and the following is happening here. So we have that 3D matrix X, and now X is a representation of our graph. And now what we have in X is that it basically X here on this axis, so it's a 3D matrix. On this axis, we indicate each of the possible relations. So this relation number 1, relation number 2, 3, 4, and so on. So this could be things like, so this person likes milk, or this person dislikes this, and so each of these relation types would be here on this axis. Then here on this front, basically, is a 2D matrix, and each of these sides basically represents all the entities. So you would have all the entities here and all the entities here. And now inside this 3D matrix, you're putting in 1 for the jth entity and ith entity in case relation K holds. Right? So if you have a person located here, if you have milk located here, and this is relation K which goes in that direction, then you're putting in this box of 1. So what you get is basically a very large matrix, which you can represent more compact as a sparse, because it's a very sparse matrix, so you can do a more compact representation. And what's going to happen in this tensor factorization is you're going to decompose it into three matrices here. Now, decomposing basically means that you have these three matrices here, which are smaller as the original one, but when you're multiplying these matrices, you're going to obtain the original again, or at least something as close as possible to the original. Now, what is special about these matrices here is that actually this matrix on your right, yeah, and this matrix on your left. Okay, that's the opposite way. So this one on your right, this one on your left, is that they're actually the same matrices, right? So this is just the same matrix. This one, it has just been twisted or been turned. So we actually only have two matrices. So if one matrix, which is representing the k relations here, this dimension is something which is fixed. And then we have here embeddings for each of the entities. And again, this dimension here is fixed. So what happens now is that you have that 3D matrix. You do this decomposition in some way, right? You get that decomposition. Now, you get these embedded matrices. They have embeddings for all of the entities. That's one thing. And the second thing which they have is if you multiply them back, it restores the original matrix. Now, you have already seen a bit about, for example, autoencoders. So it has a bit of a similar idea here. So you have the original representation. You have a smaller representation somewhere in the middle, meaning these factorized matrices. And then you can go back to the original and you try to restore it as much as you can. And what this does is because that inner representation is smaller, it needs to throw out certain things like noise, like anomalies, mistakes in your graph, but it also generalizes things. So it needs to, or what it will do as in effect is that it will, for example, predict certain edges which were not in the original graph, but which should have been. So it will actually restore missing edges that way. Now, tensor factorization is very powerful, right? So it's conceptually sort of easy. Like you have that the big matrix, you decompose it, you restore it back, and you have your link prediction. That's also what it's very good at. There are some recent works which even show that even the method which I just showed on the slide is actually extremely powerful, more powerful than some other methods. Also usually scalable because there are they make use of very powerful linear algebra operations. And they can at least encode some multi-hop information. Right? Up to some extent, they're also explainable. So you can sort of say why certain edges have been predicted. So you can sort of backtrack that. And there is some way of also including numeric attributes, something which was not really possible with the translation-based methods. Now, there's a drawback. So one of the drawbacks is that the embedding quality, so for link prediction, it works well, but for downstream machine learning tasks, this has never shown to be working very well. And again, you also, I told you, like you have stronger, or you have other matrix factorization techniques as well. And there's, again, the better the model, the less scalable it becomes. Okay, so these were the first two classes. Now we go to this last class, which is random walk-based. Now, the random walk-based methods, what they basically do is they are going to use random walks to extract the context around a certain node. So you would have a node, you start to do a random walk around it, and extract that way context for that node. Then this context is used as an input to a word embedding technique. So basically what you do is you sort of, similarly as the example we had about a cat occurring in the context of animal, here you're basically going to use similar distributional hypothesis information to embed nodes. So one way to do this is to start from a node and creating a sequence. What that means is you start from a node, you write down what the label of that node is, you do one random step to the next node. Again, you write down what edge you followed, you write down what the next the label of the next node was. Then you do that again. So you do again a random jump, you write down what that edge label was, you write down what the next node was. What you this way get is you basically get a text. Right? So you get a sentence sort of saying, okay, this person likes milk, milk is similar to cheese, and cheese contains so much fat, and so you basically get this kind of sentence. Now what you can then do is you can feed these sentences to a language model, like for example the word-to-vec model, and get embeddings for the words out. Now these words correspond again to concepts in the graph, and this way you've basically created an embedding for your graph. There are some additional tricks. So for example, you could bias the walks. So instead of just randomly jumping to locations, you could put certain weights, like extra weight to certain directions. Or you could also use graph kernels, which we didn't really go into, but basically like other ways of navigating the graph. Okay, so another technique which is rather similar, or which actually uses a similar distribution hypothesis, is to use what is called personalized PageRank. Basically means you want to, for each node, you look at a certain node in the graph and you sort of look at its neighborhood in a sense. So you sort of try to cut out a neighborhood in the graph. Now, the information about that neighborhood, so about how close these nodes are, is also fed into another type of language model, which is called GLOF. And then basically the idea is there to use a distributional hypothesis in such a way that you say that similar things, so similar nodes, would have similar context in the graph. So would have similar neighbors and similar neighbors of neighbors and so on. Now, this language model specifically optimizes for preserving analogies. So these things which you might have seen in some cases that, for example, king minus man plus woman would be equal or close to equal to queen and so on. The benefit of this model over the random walk method, which we saw before, is that it really captures a complete context. It does not just sort of randomly walk in hopes to sort of find the context. No, this really captures the complete context at once. Now, if we look at these kind of methods, they have some benefits. And one of them is that they can deal with very large graphs, right? Because they use local neighborhoods and they can very nicely cover this large graph because they only do actually small graphs. They give reasonably good embeddings, right? So they really can give you embeddings which are useful for downstream machine learning tasks, and they have a good training. Explainability is a bit on the poorer side, right? So some things are partially explainable. For example, the method I just explained with capturing this context, so you can do some sort of explanation there. There's still a lot of research needed there. And also larger context can be used with this scalable methods. Now, one thing it does not do well, that is link prediction. So it basically sort of forgets, in a sense, the original things which were in the graph, because this method is really focusing on the semantic similarity between things. Right? So it uses distributional hypothesis. So it, for example, is going to put continents together in the embedded space, while in the original graph, they were not even together at all. Okay, so this was the part 2. So this was basically on how we can take graphs, specifically nodes, and embed them into an embedded space. And then these embeddings could then be used in a next step to feed into a downstream machine learning task. So in the next part, we will start looking at graph neural networks.